Hi, we are back with section 3.5, additional applied optimization, and we are tackling basically just one example after another. So now this example has to do with minimizing travel time. So here's our setup. Alex is walking west on a sidewalk along the edge of a grassy area. This is in front of the Ed complex at the University of Oregon. So grassy area is about 200 feet east and west, so that's width, for instance, and then height is 300 feet. So Alex strolls 4 feet per second on sidewalk, but then when he's walking on grass, he slows down somewhat, so he's only going half that speed. So from the top right corner, the northwest corner, how long should he walk on sidewalk before cutting across the grass in order to reach the southwest corner in the shortest amount of time? So it's sort of given away the example title here, but the thing that we have to identify is what are we trying to do with this setup? The thing that we've been asked to find is shortest time. So we're actually minimizing time in this sense. That's the output, which is maybe a strange scenario to be in, but the question is how long should he walk on the sidewalk? Or perhaps what distance should he walk is a good place to start. Okay, so we basically got an input and an output. So the input is how long does he walk on the sidewalk, and the output is what is the shortest total distance, so shortest total time. Okay, so let's get a picture. Here's Alex up here, fittingly, it's the point A. He's going to walk some unknown distance west and then cut across the grass. So the question is, he could walk a long ways along the sidewalk and then cut across the grass. He could walk a short way, he could walk just straight across the grass. Who knows exactly yet what would minimize that travel time. So if we just use a variable to represent that, this is some distance that he walks, then this distance d along the diagonal there would be the remaining distance. But as soon as we establish what x is, then d is fixed. So I'm going to imagine somewhere along the way that I can turn d into something with some kind of expression with x's in it. Okay. So total distance is the sum of those two things, x and d together. But actually the time is what we've been instructed to find. So we're going to use this so-called DIRT formula here, distance is rate times time, and reorganize a little bit. So all we really need to do in this case is divide both sides by the rate. So if we divide both sides by the rate is out of there, and then we have that time is equal to distance over rate, just like this fraction down below. And because we still have some variables running around in here, the only thing that gets better is that while he's on the sidewalk, we know that his rate is 4 feet per second. So the time along the sidewalk portion, so I'm putting a little subscript there, is, well, distance, actually x, that's the unknown thing. That's precisely what we're trying to figure out here. And then in the denominator is the fixed speed that he moves along the sidewalk. And then very similarly, we've got that the distance he walks along the across the grass in the diagonal, but the speed is different. So now he's only moving 2 feet per second across the grass. So this is the total time required to walk across the grass piece. So we've got two things, and at the moment x and d are sort of separate, but actually they do have a connection. And the way to figure that connection out, maybe I'll back this up so I don't give it away. You know, it's like a good story. You don't want to read the end. Writing in terms of x means that we need to use the Pythagorean theorem, and that's because we have a nice right triangle up here in the corner. And we know one of the side lengths. We know that the vertical side length is 300 feet. We know that the diagonal is d, and then the last piece of information to figure out is how to represent this horizontal distance. But we know that the total distance across is 200. So if this part is x, then this must be the leftover from 200. So just as for instance, if x was 50, then this distance should be 150 because that would be 200 minus the 50 units that we had on the right side here. So since we don't know what x is, we're using that expression 200 minus x. But here's our, you see my schedule. Here's our Pythagorean theorem written out. So this would be d squared, or I guess c squared, by usual convention. We'd have that across the diagonal there. And then we'd square root it because we're really looking for d written in terms of x. And if you watch the previous video with the rancher and the enclosures in the yard, and this equation right here, this distance equation written in terms of that x, is equivalent to the perimeter equation that we had before. It's not that this is the end to the question, but it is a means. It's a way to eliminate one of the variables and get down from two variables down to just one, x. So this is a relationship between the d variable and x variable. So this is if we're thinking Pythagorean theorem again, here is c. This is a, so a squared, and then 300 is the b. So this is square root of a squared plus b squared in the Pythagorean theorem. And then just building in the fact that the time is actually really the important part. The time is distance over 2, so it's this whole thing we just came up with over 2. So this whole expression is distance right there. Okay, so the thing that we're actually trying to minimize is total time. So let's get our function. So here are the two pieces put together. This is time 1 and time 2. If we use the two expressions we just came up with, then time 1 is x over 4, that same deal. And actually, we don't really need to change this very much because we've already got x as the variable of interest. So then where the real action comes right here. We've got distance along the diagonal. Distance through the grass is that expression. All right, well, once we've got our time, the way we minimize or maximize any function is by taking its derivative and figuring out where it's 0. Technically, yes, we should also look for critical points due to f prime being undefined, but we're not going to find any interesting values in that case, in this particular problem. Okay, so derivative of that whole thing. Well, all right, let's do this bit by bit. Derivative of x over 4 is not too bad at all. That's just that 1/4. The rest of this takes a little bit of effort, though. So everything else is from this fraction. So first of all, let's say, okay, we're pulling out a 1/2. So let's not make quotient rule out of what is already a mess here, and just say, look, we've got a constant in the bottom. Dividing by 2 is the same as multiplying by 1/2. So we'll just leave that guy out. Okay, so the rest. This is a bunch of stuff to the 1/2 power. So here's all the stuff that's underneath the radical. This is one big instance of chain rule. So we get to do 1/2 times a bunch of stuff and then our new exponent is decreased, so it's down to -1/2. But if you may already be thinking about this is going to involve chain rule. All the blue stuff in here got ignored when we did power rule, so we have to tack on the derivative of this inside stuff. So all the derivative of all this, so 300 squared, that's not going to go anywhere. Derivative of a constant is 0. And then we've got chain rule inside of this because we've got 200 minus x all squared. And if I could truly ruin this with one more color, then we could say, look, here's the inside part. We need the derivative of that taken right there. One last instance of chain rule. So it was 2 times this stuff to the 1 in power. So there's all that piece. And then times the chain rule portion. Derivative of 200 minus x is -1. Let's try to tidy a little bit. Just to track things in the same color, perhaps. We've got that 1/4 getting subtracted over. This is our first step in trying to get x by itself. But notice it's in a couple of places here, so we're going to have to get creative in our solving strategy. With a little simplification, we can combine some of these things. You might notice if we've got 2 times a 1/2, those are going to kill each other off. Since this 2 is actually a factor of this whole big monstrous thing, and so is the 1/2, those are going to kill each other off. So we still have the 1/2 out in front here. And it's negative because there's and the -1 from that chain rule just getting pulled out in front. So same deal there. And then everybody else is the same. We still have 200 minus x. We still have all this stuff to the -1/2 power. All right, we're on our way. Continuing to move stuff around, if we go back just a sec, the next thing that we'd probably want to do is get rid of this -1/2 factor. If we multiply both sides by -2, we get just 1/2 on the left side, and no other constants getting multiplied to this whole big deal. Then, this is in the denominator, and maybe we could, because of this negative exponent, so maybe we could employ the everybody hates fractions policy and multiply both sides by the square root of all this junk. That's going to make this all disappear from the left side and give us that same power 1/2 on this on the right side, since we had to treat both sides the same, multiply both sides by the square root of all that nonsense. Okay, so the advantage of this is that I would really like to get this square root, this x out of the square root. And the only way that's going to happen is if we can get this square root to go away, and we can do that by squaring everybody. So this shows up in the next line anyway, but we were separating, we kind of peeled off this square root in an effort to get it on another side, but it turns out we're gonna need all our x's someplace. Anyway, here we are. We're gonna square it all. I should be really careful about this. I can't be preferential about this. Everybody's got to get squared, so the 1/2 gets squared as well. Okay, so there we see that happening, and then 1/2 squared out in front is going to give us 1/4. So it's important that we remember that piece. And what has happened in this case is that the square root is out of the picture. So now I have to make sure that 1/4 gets multiplied to 200 minus x squared, and also to this other term. On the right side, I'm biding my time a little bit. I know this needs to get squared. Maybe I have to multiply it all out, but I'm just going to kind of hold on to it as long as possible. Okay, so now we're going to do, we'll bring this back just for a sec. So this is some combining of like terms. So we'll get rid of some color when we go back. Notice that these things, as weird as they may look, are like terms. There's 1/4 of this thing, 200 minus x squared. Here is 1 of 200 minus x squared. So if we subtract this over, we're actually rewarded for not having multiplied this whole thing out. Because now if I have 1 of something minus 1/4 of that thing, now we have 3/4 of it. And I think I did the subtraction in the slide the other way. So you've got negative on one side and the negative on the other, but it's equivalent. We're going to make those negatives go away. So multiply both sides, or perhaps you could think divide both sides by the negative 3/4. And then since it's just a number on the right side, if we divide all this by negative 3/4, we'll get something concrete out of it. We're almost there. Last things to do, square root to get rid of the square. And then if we add x and subtract this whole square root of 30,000 deal, then we'll finally get values for x. So I don't get any negative numbers out of this. We get 26.79 or 373.21. So neither of those look suspicious right off the bat. However, the width of the field is only 200 feet. So 373 just isn't a worthwhile number. So 26.79 is the only one that actually matters to us. So this is out of the domain consideration for this particular question. So 26.79 is our most logical chance to find a minimum time. Now, okay, so one of the ways that we check for absolute extrema is to use the second derivative test for absolute extrema. But, oh man, it was already hard enough to get the first derivative. Taking the second derivative of that huge square rooty thing sounds like way too much work. So instead, we're just going to do the old-fashioned way. We're going to find the critical points, which we just did, and then we're going to compare them against the endpoints. So he could walk 0 feet along the sidewalk. That's the lowest value we could run into. Or we could walk all the way across the field and then go straight down, vertically, walk north and south along the edge. So these are the two endpoints to consider against that. Although, we should be pretty confident at this point that this thing, 26.79, is actually going to be our minimum. But we'll do the pro forma thing and check it out. So let's take a look. Here's our table of values. Here's the x's that we wanted to compare. And this is going all the way back to our total time function. So plugging these three values in, this is a great thing for a calculator to help us out with. I think it seems clear, although it's not by much. This actually is the lowest value. So we're confirming that's an absolute minimum. And just conclusion in words, so if he walks for about 26.79 feet and then goes southwest straight to the southwest corner, then he'll spend that minimum time, which is about 179.9 seconds walking. Okay, so that's it for that one. We'll be back with one more business/econ related example from this section. Thanks for watching.